It's 2:02 a.m.
Yep.
You're staring at your IDE. The screen glare is practically burning a hole in your retinas, and you're trying to get a promising lightweight AI model off the ground.
We've all been there.
Right. Let's say you're building a custom coding assistant specifically for your company's massive, undocumented, totally proprietary legacy code base.
Ooh, the dream project.
Yeah, exactly. But you can't just send all that sensitive code out to some external API. You need a local model.
Absolutely. Security first.
So you've got the architecture mapped out, you've got the compute allocated. It's like you've built this beautifully engineered high-performance sports car, but you're just sitting in the garage.
Because you don't have the fuel?
Exactly. You can't afford the highly refined racing fuel it needs to actually run. And in machine learning, that racing fuel is, well, it's high-quality training data.
It is the silent killer of enterprise AI projects. I mean, everyone focuses on shiny new model architectures or clever optimization tricks.
Right.
But the harsh reality is the data bottleneck usually stops an engineering team completely dead in their tracks. We treat AI development like it's pure code, but under the hood, it's really an exercise in curating knowledge at scale.
Which is wild when you think about it.
It is. To build that internal coding assistant, you'd need, gosh, tens of thousands of perfect handcrafted examples of developers interacting with your internal APIs.
Finding, cleaning, or paying developers to manually write like 50,000 flawless prompt and response pairs, that is agonizingly slow.
And staggeringly expensive.
Yeah, it's a total non-starter. But tonight, for everyone burning the midnight oil, compiling code while the rest of the world sleeps, we have a deep dive that feels kind of like finding a developer cheat code.
It really does.
We're pulling from the LLM Mastery series, specifically looking at data synthesis. Okay, let's unpack this.
Let's do it.
The mission tonight is to help you, the listener, understand how to completely bypass that massive dataset cost, the advanced techniques to ensure that synthetic data is actually usable, and this is crucial, the hidden architectural traps that will absolutely tank your model in production.
Yeah, those traps are brutal.
So to start, what is the core premise here?
So the foundational premise of data synthesis is automating the creation of training data, but doing it using existing massive language models.
Okay.
You take a state-of-the-art model, something that costs millions to train, and has essentially read the entire internet.
Right.
And you use it as an automated teacher. You write a script that prompts this massive model to generate highly accurate coding examples, documentation, logic puzzles, all of that.
Okay, I follow.
Then you capture that output and use it to train your much smaller, cheaper, local 7 billion parameter model.
To put that in pure engineering terms, it's kind of like having your most expensive principal staff engineer sit down and write this enormous, comprehensive suite of integration tests and docs.
Exactly.
And they're doing it purely so a junior developer can study that localized code base and get up to speed without constantly tapping the senior dev on the shoulder.
That is a perfect analogy. You're downloading the senior developer's brain into a localized, cheap repository.
Right, which is huge for costs.
Exactly. It solves the core problem of economics versus performance. Because, you simply can't deploy a trillion parameter senior engineer model locally on every developer's laptop in your company.
Oh, the compute requirements would be
Catastrophic.
Yep. Okay.
The latency alone would make it unusable. By synthesizing the data, you get the localized efficiency of a small model, but it's imbued with the distilled, generalized reasoning capabilities of the massive one.
You transfer the logic without taking on the operational overhead.
Precisely.
Okay, and here is where my developer brain immediately hits a snag. If I'm writing a Python script to hit that massive model's API, say 50,000 times, asking it for coding challenges based on our legacy code base,
Right.
It's just going to spit out 50,000 variations of a basic for loop or a simple API fetch.
It'll be incredibly repetitive.
Yeah. If the dataset only contains basic data, the small model only learns to solve basic problems. We need to somehow force the big model to generate a curriculum of increasing difficulty.
The sources outline a very specific technique for this called Evol-Instruct.
Evol-Instruct, okay.
Yeah, because if you naively sample a large model in a loop, it mathematically regresses to the mean.
Meaning it just gets boring.
Exactly. It outputs the most highly probable average vanilla responses. Evol-Instruct combats that by programmatically scaling the complexity. It systematically evolves simple instructions into highly complex architectural problems.
I was looking at the mechanics of this, and it immediately made me think of video game level design.
Oh, how so?
Well, you never drop a player straight into the final boss, right? Level 1 is always simple. It's the hello world instruction.
Right, the tutorial level.
Yeah, something like write a Python script to fetch a user profile from our internal API. But I want to understand the actual programmatic loop here. How does a script force an LLM to make a prompt progressively harder?
What's fascinating here is that it uses metaprompting. You aren't just asking the model for a harder question. You are passing the previous output back into the LLM, along with a specific mutation strategy.
A mutation strategy.
Yeah. In your Python script, you have an array of mutation prompts. One might be, take this base instruction and add a real-world constraint.
Okay.
Another might be, deepen the required algorithmic reasoning, or maybe complicate the input format.
So the script takes the level 1 prompt, feeds it to the big model with the add a constraint mutation, and the model spits out level 2.
Exactly.
Which would be like, fetch a user profile, but implement a retry mechanism with exponential backoff for rate limits.
There you go. Then the script captures level 2, selects a new mutation strategy, like, say, deepen the reasoning, and passes it back again.
Oh, wow. So now level 3 becomes fetch a user profile with exponential backoff, but handle concurrent requests using a Syncio and managed state across distributed cache nodes.
Yep. You iterate this process. The result is a synthetic dataset that spans the entire spectrum of difficulty, from basic syntax to complex, multi-threaded architectural constraints.
So the small model isn't just learning the syntax of the company's API.
No, not at all.
It's learning how to overcome complex engineering obstacles.
Exactly. Because a human software engineer doesn't hit the senior level by resolving the same simple CSS bug 1,000 times. Right?
I hope not.
Right. They level up by tackling progressively harder systems problems, dealing with race conditions, memory leaks, complex state management. By feeding your local model this artificially scaled complexity, the Evol-Instruct curriculum forces the neural network to develop much stronger internal representations of logic.
It learns the underlying mechanics of reasoning through constraints.
Precisely.
Okay, wait, I'm confused about something here.
Sure, go ahead.
If we set up this automated pipeline to generate 50,000 increasingly complex, mutated coding tasks,
Right.
some of them are going to be absolute garbage.
Oh, absolutely.
The large model is going to hallucinate. It'll generate a constraint that logically contradicts itself, or it'll write a solution using an internal library that doesn't actually exist.
The dreaded hallucinated library, yeah.
If we feed 10,000 hallucinated broken scripts into our small model, we're poisoning our own well. How do we build automated quality assurance for a pipeline that generates data this complex?
You've hit on the most critical vulnerability in the pipeline. You can never blindly accept synthesized data.
Right.
The sources emphasize two powerful techniques that act as the automated QA layer: rejection sampling and constitutional AI generation.
Okay, let's break those down.
Sure. Rejection sampling addresses the probability problem directly.
Looking at rejection sampling, to me, it feels functionally identical to running a brute force fuzzing test in CI/CD.
Oh, that's an interesting way to put it.
Yeah, in fuzzing, you throw thousands of malformed inputs at a system just to see what survives and what crashes.
Right.
With rejection sampling, instead of prompting the large model to generate one answer to that level 3 Asensio problem, you ask it to generate like 20 different answers.
Yes.
Then you run them through an automated test, maybe actually executing the code in an isolated sandbox to see if it compiles, or using another model to score the outputs. You throw away the 19 failures and only keep the single output that passes.
If we connect this to the bigger picture of probability mechanics, large language models are essentially predicting the next token based on a probability distribution.
Right.
If you generate just one answer, you are locked into whatever path the model wandered down on that specific run.
Which might lead straight to a hallucination.
Exactly. By generating 20 variations, you are actively exploring the wider latent space of the model's knowledge. You give it multiple independent chances to navigate toward the optimal logical path.
Oh, I see.
Generating many and rigorously evaluating them acts as a massive statistical filter. It drastically raises the baseline quality of your dataset.
Okay, so that's rejection sampling. Then there is constitutional AI, which approaches quality control differently.
Right, it's a different angle.
To me, this sounds like setting up an incredibly strict automated linter in your deployment pipeline. You try to merge your code, and the pipeline immediately rejects it because you violated a memory safety guideline, sending it back with a list of errors you have to fix.
That's a great comparison.
And here is where I need some pushback from you.
Okay.
If the large model generated a flawed, insecure piece of code the first time because that code was statistically probable,
Yes.
Why on earth would we trust that same model to catch its own mistake during a critique phase?
Yeah.
Doesn't it have the exact same blind
It
spots?
seems completely counterintuitive, I know.
Oh,
But generating text and evaluating text require entirely different cognitive loads and attention mechanisms within the transformer architecture.
really? How so?
Generating is an open-ended, auto-regressive process. The model is blindly stepping forward one token at a time. Evaluating is a constrained bidirectional process. When you give the model a constitution, like a hard set of principles, say, the code must be secure, avoid race conditions, and not use deprecated libraries, you are giving it explicit guardrails to check against an existing block of text.
Oh, so the attention mechanism is focused purely on finding violations of those rules rather than trying to invent the next line of code.
Yes, the pipeline looks like this. The model generates the initial synthetic response.
Right.
You then prompt the model again, providing its own output alongside the constitution, and ask it to act as a code reviewer.
It critiques its own work.
Exactly. It might output something like, looking at the previous code, the use of the request library without a timeout parameter violates the security reliability principle.
Wow, okay.
Finally, you prompt it a third time, passing the original output and the critique, and instruct it to rewrite the code, fixing that specific flaw.
So it's a closed-loop self-correction system.
Exactly. It forces the data to align with hard engineering rules before it ever touches your training set.
Man, we've architected this incredible machine here.
We really have.
We use the big model to generate data, Evol-Instruct to scale the difficulty from a basic fetch script to a distributed microservice,
Yep.
and then rejection sampling and constitutional AI to aggressively filter, compile, and lint the outputs so our small model only learns from pristine code.
Sounds bulletproof, right?
It does sound bulletproof.
Right.
But here's where it gets really interesting.
Okay.
The source material drops a massive warning label on this entire ecosystem. There are catastrophic bugs this automated loop can introduce if you aren't paying attention,
Very true.
namely data contamination and model collapse. Let's look at data contamination first. This is basically the equivalent of accidentally committing the answers to the final exam into an open source study guide repository.
It all comes down to how we evaluate the intelligence of a newly trained model. Engineers use standardized benchmarks, right?
Yeah.
Massive data sets of coding problems and logic puzzles designed to score a model's capabilities.
Right, the final exam.
The problem is that the massive state-of-the-art model generating your synthetic data has scraped the entire internet. It has already ingested those exact evaluation benchmarks during its own training.
Oh, no. So if you aren't rigorously filtering your synthetic pipeline, the large model might generate training examples that are mathematically identical to the questions on the benchmark test.
Exactly.
You finish training your small local model, run it against the evaluation suite, and it scores a 99%.
You pop champagne thinking you've built a genius coding assistant.
Right. But in reality, the model just memorized the answer key.
Yep. It creates a complete illusion of progress. And the moment a developer asks it to solve a novel, undocumented bug in production,
The model completely falls apart.
it invalidates your entire engineering cycle.
That's terrifying.
It is. But model collapse is an even more existential threat to the architecture.
Okay, what is model collapse?
This raises an important question. The sources define it as the...
Successive generations.
Okay. To understand why this happens, you have to look at the difference between human data and synthetic data. Human data like code on GitHub, Stack Overflow discussions, obscure engineering blogs, it's incredibly chaotic.
Yeah, humans are messy.
Exactly. It has massive variance. Humans write weird edge cases, creative hacks, and unexpected, brilliant workarounds.
And synthetic data, even with Evol-Instruct trying to force complexity, is still mathematically biased toward being average.
Yes.
It smooths out the chaotic edges of human thought.
It does.
It's like, okay, it's like saving a JPEG image over and over again.
It's a brilliant way to think about it.
Right. The first time you compress and save it, you lose a tiny bit of pixel data. It looks fine. But if you compress and save that exact same JPEG 1,000 times, the compression artifacts compound.
Yep.
You're left with this blocky, unrecognizable mess. You completely lose the high-fidelity resolution of the original photograph.
To ground that in the actual mathematics of the neural network, what you are doing is truncating the tails of the probability distribution.
Okay, unpack that for me.
In human data, rare tokens, the weird, creative, highly specific solutions, they have a low but non-zero probability.
Right.
Because they have low probability, A synthetic model rarely, if ever, samples them when generating data. It sticks to the fat middle of the bell curve.
So if Model A synthesizes data to train Model B, those rare tokens are just
Got
excluded.
gone. And then when Model B generates data to train Model C, the distribution narrows even further.
Oh, wow.
Over just 3 or 4 generations, the tails of the probability distribution effectively drop to absolute zero. The model loses the ability to comprehend or generate rare, complex logic.
The vocabulary shrinks. The reasoning flattens.
And eventually, the network devolves into outputting repetitive, nonsensical garbage. The model's fundamental reasoning architecture collapses because it has been starved of the rich, chaotic variance that only exists in human-generated data.
So what does this all mean? We've laid out the cost hack of the century.
We have.
We've built the automated QA filters with rejection sampling and constitutional AI, and we've stared into the abyss of benchmark contamination and probability collapse.
A busy night.
Very busy. If an engineer is listening to this right now, trying to figure out how to actually deploy this custom coding assistant in their stack tomorrow morning, what is the final architectural recommendation from the sources?
The overarching principle, the golden rule the sources insist on, is that synthetic data is exclusively a supplement to real human data, never a complete replacement.
Never a replacement.
Never. Human data is the indispensable bedrock of your training pipeline. You must use human-curated data to teach the model the ground truth of creativity, the unexpected variance, the chaotic brilliance of real engineering.
Okay.
You deploy synthetic data strategically to scale up specific domains, to bulk out your instruction following capabilities, or to fill in missing gaps where human data is just too expensive to procure.
It's a strictly hybrid architecture.
Yes. That hybrid approach perfectly completes the modern fine-tuning stack every machine learning engineer needs to understand.
Right. You utilize efficient fine-tuning methods like LoRa and QLoRa for compute efficiency. You combine those with data strategies like instruction tuning to format the assistant, domain adaptation to teach your legacy codebase, and data synthesis to cost-effectively scale the volume.
Wait, for those who haven't set up a local model recently, remind us what LoRa is doing under the hood. That's low-rank adaptation, right? Just freezing the main weights of the network.
That's the core mechanism, yeah. Instead of updating all 7 billion parameters of your local model, which requires massive GPU clusters.
Which nobody has at home.
Exactly. LoRa freezes the original weights and injects small, trainable rank decomposition matrices into the transformer layers.
So you are only training a tiny fraction of the parameter.
Yep. When you put the whole stack together, LoRa allowing you to train on a single consumer GPU and a hybrid data pipeline blending human ground truth with constitutionally filtered synthetic data, you achieve an incredibly robust, cost-effective development cycle. It's a completely different paradigm. You aren't just blindly dumping massive CSV files of data into a neural net anymore.
Not at all.
You are architecting a highly specific, carefully balanced learning environment. You're harnessing the raw, chaotic genius of human developers alongside the tireless, scalable, but mathematically fragile generation engines of AI.
It gives an engineering team an unprecedented amount of leverage, but it demands an entirely new level of discipline to keep the pipeline stable.
The role of the machine learning engineer is evolving into the role of a highly rigorous data curator.
Absolutely. Writing the PyTorch script to train the model is often just a few dozen lines of code.
Right.
Building the pipeline to ensure the dataset is uncontaminated by benchmarks, constitutionally sound, and mathematically anchored by human variance. That is where the actual engineering happens today.
That leads to a final thought I want to leave you with tonight. Something to ponder as you tab back over to your IDE and start writing your next function. The sources make it mathematically clear that model collapse is a certainty if we stray too far from the chaotic variance of human data. Synthetic data needs pristine, human-generated code to act as its anchor to reality.
Right.
But if software engineers worldwide are increasingly relying on AI assistants like Copilot to write their boilerplate, to auto-complete their functions, and to solve their bugs.
Oh, I see where you're going with this.
And those same AI models desperately need pristine, purely human code to avoid collapsing in on themselves. Are we slowly depleting the very resource of human data required to train the next generation of models?
Bro.
If every pull request becomes a hybrid of human and AI generation, Where do we find the uncompressed, high-fidelity human logic tomorrow?
It's a fascinating and deeply concerning architectural paradox.
Remember, you can build the most beautiful, optimized engine in the world, but if you don't respect the data you put into it, you're never making it out of the garage. Thank you for joining us on this late-night deep dive. Keep compiling, keep experimenting, and we will catch you on the next one.